Lesson 4.1 on extreme values. A couple of things we're going to try to accomplish in this lesson. First, you need to know what extreme values are. Um, also know absolute or global extrema, local or relative extrema. Define and find critical points or values. All right, we start by reviewing intervals. Let A and B be real numbers. So A could be like 4, B could be like 9. Then we call this a close interval, and it means that it includes endpoints, A and B. So then an example of that would be 4, 9. So any items or any numbers between 4 and 9 is true, but we also include 4 and 9. Open interval, which is we use parentheses to represent open interval, it does not include the endpoints. So in our example, this would be an open interval and it doesn't include the endpoints. We can also have what's called half open. This is a half open. So it's open on the left side or open on the right side. It includes one or the other endpoints. Graphically, one close endpoint and one open circle. So this is an example of a close interval. So we say this is between -1 and 2 because we include -1 and we also include 2. This is an example of open interval. We don't include the endpoints. So -1 and 2 are not included. This is an example of half open. We include the left endpoint, but not the right endpoint. Okay. Awesome. So we begin by reviewing intervals, and now we get to one of the main point of this lesson, which is on extreme values or extrema of a function. So extreme values or extrema may be used interchangeably to relate to a specific value of function f. Extreme values are basically the maximum or the minimum values of a function or around a specific area. So in this example right here, extreme values would be like the y value of point A because it is the minimum value of the function. It is also the y value of point B. Remember that every point has an x and a y value, right? So the y value are what we call the extreme values of a specific point. Another extreme value is the y value of point C, the y value of point D, the y value of point E, the y value of point F. So what are extreme values? Well, they are either the maximum or the minimum values. Notice that A is a minimum value, B is a maximum value. Now C, it's not the lowest value, but it's a minimum value compared to any value around its neighborhood. Around its neighborhood, this is the lowest value. D is not the highest value. It's not, we don't call it like the highest value of the function, but it is a maximum value around its neighborhood. So we call like point C and point D, more specifically, we call point D local maximum value because it's only the maximum value locally, all right? E would be another example of an example of a local minimum value because it's a small value, but just within a specific neighborhood. F is an example of a local maximum value. It's a maximum value, but just locally, not globally, not compared to everything. All right. So in general, when we say extreme values, we're looking for the maximum or the minimum values of the functions. And it could be extreme value, could be we call it global max, or local max. It could also be global minimum or local minimum. And I think I will go into a bit more details in the next page. All right. But for now, in this first page, when people ask for the extreme values, they're asking for what is the largest value of all, or what is the largest value within a neighborhood, what is the smallest value of all, and what is the smallest value within a neighborhood. So if I were to label this, I would label this guy as my global. Fix my pen here, guys. Global min. This is the lowest value of all, right? Point B would be my global max. This point C would be my local min. Okay? Local max. Local min. And also local maximum. All right? So here it is, guys. Extreme values can be broken up into two parts. Extreme values can be either absolute or global extrema. And what that means is it could include the highest point or the lowest point. So absolute extrema can be either global maximum or global minimum. When we use the word global, we're saying the highest of all, right? When we use the word global minimum, we're saying the lowest of all the points. Okay. Extreme value can also be local relative extrema, so it could be like local maximum or local minimum. Okay. Now, what is global max? Well, global max, so let me kind of define this for you. Say f at A is a global max if it is the largest value, compared to all the value in the function. So this is the largest value of all the values. F of A is a global min if f of A is the smallest value compared to all the y values in the function. So maybe we can say for all x. Okay. What about local max? Well, f of A is a local max if f of A is larger than f of x for all x within a specific neighborhood. So it's within a specific region. Okay. Same thing, f of A is a local min if f of A is less than f of x for all x within a specific region. Okay, so to summarize what we have accomplished so far, we're trying to understand what are extreme values. And extreme values, they can be either the largest value or the smallest value. Okay, they can also be the largest value within a small neighborhood or the smallest value within a small neighborhood. And all of those categorize extreme values. All right. Now, hopefully you might have figured this out by now, but extreme values, they take place, they occur at the turning points and also at the endpoints. All right. And here's the cool thing, guys. The turning point is where the derivative equals to 0. And that's how it kind of ties back to derivative. Okay, so let's take a look at the first problem. The graph, given the graph of f, here it is, identify any absolute extreme and local extrema. So this graph here will go on forever. I'm going to put arrows on here so that it goes on forever. So the only extreme values it has takes place right here, okay? So it says identify any absolute extreme and local extreme. So the absolute maximum, it's gonna be 3. It's always the y value, okay? Absolute max is gonna be 3. Local max, it's also 3. It's also 3. It does not have an absolute min or local min. It does not have a minimum value because if you look carefully, the graph would just kind of continue to go down forever. So it does not really have a minimum value. It has a maximum value. So every absolute max is also a local min. But I'm sorry, every absolute maximum is also a local max. But a local max does not necessarily mean that it's an absolute max. Okay, let's take a look at example number 2. Okay, I'm going to assume that the graph has arrows on there. What are the absolute extrema? In other words, what are the largest and the smallest? And local extrema, what are the largest within a neighborhood, within a specific neighborhood? What are the smallest within a specific neighborhood? These points, these values happens at a turning point. So because the graph has arrows, it's going to continue to climb forever. This point right here is a absolute min because it is the lowest point compared to all the lowest point. This point right here is a local min. So why don't we start out by listing all the minimums? So I found the absolute minimum value, which is the lowest of all the lowest points. That happens to be -1, 2, 3. I'm going to call that -4. We also have a local min. Remember that absolute min is also a local min, so -4 is one of those. And then there's another one over here, so 1, 2, about, I would say, -2.5. That's also another local min. Absolute maximum, these has arrows, it's going to continue to climb. So really, the function does not have an absolute maximum. However, it does have a local maximum, and that local maximum exists right there, happens to be -1. Remember that these are the y value, and they're -1. Now, notice that not all functions have extreme values. Not all functions have extreme values. For example, the function of a line goes on forever, and it does not have extreme value because it doesn't have the highest value. The value continue to climb, and it doesn't really have the lowest value. So this function right here, no extreme value. Okay. Here's another function. This function does not have extreme value either. It does not have a minimum value. It doesn't have a maximum value because it continues to keep going down forever. It also continues to go up forever, so it doesn't have a extreme value. Now you might wonder, well, what about this value right here? Isn't that an extreme value? And the answer is no, because if we consider this as being its neighborhood, then yes, truly to the left of the point, it is the highest compared to any point within its left neighborhood. However, to the right side, it is considered the lowest compared to any point to the right of it. Therefore, that point lies like in the middle, and it's really not the highest, it's really not the lowest, because when we consider the neighborhood, we have to consider the neighborhood on the left side and the neighborhood on the right side in order for it to be considered like a local max or a local min. In this case, this function also does not have an extreme value. So notice that here's the line, it doesn't really have an extreme value. Here's the function x cubed, and it doesn't have any extreme values. All right. And if you look at this function here, guys, I'm going to put arrows on these functions because they are the domain is all real numbers. These are the type of functions we're looking at. This function does not have extreme values either, because if you look carefully at this point is discontinuous. There's a hole there, so it is not defined there, and the function does continue to go down forever, so it doesn't have any extreme value. No, we can't say there's a highest point or there's a lowest point for that function. So you might wonder, well, what type of function have extreme values? Well, it turns out that it's actually very simple. For a function to have extreme value, the function has to be continuous. So discontinuous is a no-no, okay? And in addition, the function has to be on a close interval. What does that mean? Well, it means that the domain can't be all real numbers. The domain can't be all real numbers, okay? So, this theorem tells us that if a function is continuous on a closed interval, then it is guaranteed, guys, it is guaranteed to have both a maximum, an absolute maximum, and an absolute minimum value on A and B. Period. Let me give you an example. So let's say if this is your A, and this is point over here is your B. I'm just gonna randomly sketch a function right here. I'm gonna randomly sketch a continuous function right here. Okay, that's a continuous function on A and B on a closed interval. Notice that the theorem guarantees that there has to be an absolute max. The absolute max will exist right here. And the function guarantees that there's an absolute min, and the absolute min exists right there. Okay, absolute min. Okay, so any continuous function on a closed interval has to have an absolute max and absolute min. It doesn't matter how you draw it, it's still going to be true. Okay, you might draw it like this. It doesn't matter how you draw it, it's going to be true. See, this is a continuous function on a closed interval A and B. Clearly it has a maximum. This is your absolute max. And then this is your absolute minimum value. Okay, so in order for a function to have both absolute maximum and absolute minimum value. It has to be continuous on a closed interval, period. Awesome. Now, what are critical points? Well, critical points, the easiest way for me to define critical points, to help you understand critical points, it is the points where the function makes a turn. Okay? So, this example right here, guys, this point right here would be a critical point. The point x equals to 1 would be a critical point. The point x equals to 4 would be a critical point. Okay? So, critical point value are the x values where the derivative at that point equals to 0. That's the definition of critical points. The way how we can probably relate to critical points is those are the points where the graph makes a turn, because where the graph makes a turn, derivative equals to 0. Okay? Now, how do you find a critical point if we have a function? Well, to find the critical point, it's actually pretty simple. You start by setting the derivative equal to 0. So set f prime x equals to 0 and solve for x. Find the x values where the derivative is, so it was a bit incomplete when I tell you that the critical points are the x values where f prime equals to 0. I should have added in, it's also the x values where f prime is undefined. It's also undefined. Okay? So let's say if you're looking for critical points, we need to set the derivative equals to 0 and solve for x. It's one of the options. Or we find the x values where the derivative is undefined, and that's usually setting the denominator equal to 0 and solve. Okay? Make sure that the x values are in the domain of the original function. So let's go ahead and find some critical points here. Given these three problems, find the critical points for these three problems. So the first thing we do to find the critical points is we take the derivative, or we find the derivative function by taking the derivative of the original function. That's 6x minus 6. And to find the critical points, we set the derivative equal to 0 and solve. So I want to know at what x value does the derivative equal to 0? And remember that derivative relates to slope, right? So I'm just looking to see where the slope equals to 0. And it turns out that it is where x equals to 1. When x equals to 1, the derivative equals to 0. Well, when x equals to 1, right, the slope is equal to 0. And that's what we call a critical point, the point where the graph makes a turn. Okay, good. Look at the function. Look at this function, g equals to x to the 2/3. We begin by finding its derivative function. If you subtract the original number by 1, we have negative 1/3, like that. Okay? And remember that that is usually written, if we write in positive exponent, it would look like this. And so also get used to writing in positive exponent, because from now on, you're going to have to try to find the critical points. And when you write it in positive exponent, it is easier to find the critical point. So how do we find the critical points? First of all, we set the function equals to 0 we want to know is the derivative equals to 0 anywhere? Are there any x value where the derivative equals to 0? So we set the function equals to 0, and then we ask ourselves, what x value makes the function equals to 0? And there's none. There's no way to find an x value where the derivative equals to 0. So none. Okay. In other words, the function doesn't really have a smooth turn. It doesn't really have a derivative equals to 0 anywhere. The next question that we want to come across is, this is the derivative function. Is the derivative function undefined anywhere? In other words, are there any points, are there any x value where the function is undefined? And there is. Remember that the derivative is undefined when the denominator equals to 0, right? So we know that this function is undefined when the denominator equals to 0. And the only way for this statement to be true is when x equals to 0. So at x equals to 0, the function's undefined. That is also a critical point. So let me summarize. To find critical points, two ways. You either find where the derivative equals to 0, and you find the x value where the derivative is undefined. We try to find where the x value where the derivative equals to 0, but there was none. So we went and we found the x values where the function is undefined. And it's undefined when that equals to 0, the bottom equals to 0, the bottom equals to 0 when x equals to 0. So our critical point is just x equals to 0. It's just one number, x equals to 0. Okay. Awesome. Part C, the derivative of, find the critical point of this function. Start by finding the derivative. We are going to have to use quotient rule here. So low. Notice that low has two terms, so I put it in parentheses. Low d high minus high d low minus high d low. D low is 1, so I don't have to do anything, over low square. So guess what? I'm going to have 2x squared minus x squared. That leaves me with 1x squared minus 6x over x minus 3 squared. So I need to, or I want to find my derivative. I want to find my critical points. So I begin by setting my derivative function equals to 0, and I ask myself, are there any x value that makes the function equals to 0? And the only thing we have to be concerned with is the numerator, because when the numerator equals to 0, then the whole thing equals to 0. So we take the numerator and we set that equal to 0, and then we solve by factoring. And it turns out that this is true when x equals to 0 or x equals to 6. So that's one way to find the critical points. So far we found 2 of them. And then we go back to this problem and we ask ourselves, is the function undefined anywhere? And to find whether or not the function is undefined, we take the bottom and we set it equal to 0, because if the bottom is 0, then the function is undefined. And so by doing just a bit of algebra 1 math here, you're going to see that the function is undefined when x equals to 3. Right? When x equals to 3, that equals to 0. So this equals to 0, the function is undefined. So guess what? We found our critical points. They are 0, 3, and 6. These are the points where the graph turns, or where the graph has a sharp corner. Because remember that derivative is undefined when the graph has a sharp corner. It doesn't turn nicely. It looks like this. It looks jagged, and therefore its derivative is undefined. But that could also be a maximum point. Okay, awesome. We're almost done, guys. Hang in there. This is kind of long, but this is the last page. So why is finding the critical points important? Well, it turns out that the critical points are the location where extreme values are gonna occur. So in order to find the extreme values, we're gonna need to know where the critical points are. Okay, so the following steps will show you how to use the critical points to find the extreme values, because that's our main goal of this lesson. So to find the extreme values, we begin by finding the critical point, and that's, that's find f prime, find the derivative function, and then set f prime equals to 0 and solve, okay, and so on and so forth. And also check to see where it's undefined. That's how we find the critical point. Once we have found the critical points, then we find the extreme values by calculating the function value at the critical points, and we also check the endpoints, because the extreme values can also occur at the endpoints. And the way how we calculate the function value is we substitute each critical point into the original function, and substitute the endpoints into the original function. Determine the largest and the smallest y value from our results in step 2a and b. Write out the absolute maximum and the absolute minimum as the y value. All right, so it is not as bad as you think. Let me show you how easy it is to find the absolute maximum and the absolute minimum for this problem. We got this function right here that I graphed for you. By looking at it, guys, from the interval 0 to 6, we can easily find the absolute max and the absolute min. We know that the absolute maximum occurs at the right endpoint, which is right here, and it's about I would say 48, 49. That's what I'm guessing from what I drew here. The absolute minimum happens right here, guys. It is a little bit larger than -10. Okay, but we're going to use analytical method to find the exact value. So how do we do this? Well, the first thing we do is we find the critical points. And to find the critical point, we begin by finding the derivative function, which happens to be 6x squared minus 30x minus plus 24. Okay, so in step 1, we find the derivative function. In step 2, we set that equal to 0. And then we solve for x to find out the location where the derivative equals to 0. The good news here is that we can divide everything by 6, because 6 is a common factor. So if you divide everything by 6, you get 0. If you divide 0 by 6, you get 0. You divide that by 6, you get x squared. Divide that by 6, you get 5. Divide by 6, you get 4. And the nice thing is we can factor this function easily. That tells us that our critical points, we found our critical points, they're at 1 and 4. So here's 1, makes sense. And here's 4. Those are our critical points. Those are the point where the derivative equals to 0. Okay? And we know that the extreme values will occur at either the critical points or the endpoints. So in order for us to find the absolute maximum or absolute minimum, we have to substitute each critical point into the original function. So I am gonna find f of 1. And if we plug in f of 1, we get 2 minus 15 plus 24 plus 7. That comes out to be negative 13, negative 13, 24, take away negative 13, that leaves you with 11. 11 plus 7 is 18. So f of 1 is equal to 18. So 118, that makes sense, right? We also need to check f of 4. And if we plug that in, we're going to get 2. We plug 4 in there. 4 times 4 times 4. So 16 times 4 is going to be 64. 64 times 2, that's 128. So we got 128 minus 16 times 15. 16 times 15. I am kind of lazy right now, so I'm just going to use my calculator. So 16 times 15. 16 times 15. Let me pull up my calculator real quick here, guys. Calculator. 16 times 15. 240. Plus 24 times 4. That's 96. Plus 7. And then I take 128 minus 240 plus 96 plus 7. That